All right, so what this part of the lecture is supposed to be is an example that builds our Stan model from before into the full analysis for the diet data. As you remember, in the diet data file, we had different predictors. We had the height of an individual in inches, and we had the diet group an individual went into. The diet group, there were 3 different groups for that as well. And so what I was going to do in this section of code that I mistakenly didn't include, and I apologize for that, but I'll update that when we're done, is to walk through the process of building the entire model itself. Right now I'm installing a package, and evidently it's going to take its sweet time installing, so I may just stop that. Here, what we're going to do, I got to install another package. There we go. Okay, so let's read in the diet data itself. Remember, we started our last class with these data. I centered my height variable. But if we were to form a linear model with this, here's how the linear model might work. All right, we would say our weight in pounds is equal to our height. We're going to predict it with height. We're going to predict it with a group variable, like a dummy code, a factor variable for diet group. And we may have an interaction of height with diet group itself. So that is a typical linear model. Does anybody have any thoughts on that? Does that sound reasonable for our data? If you were in the old days, we would call this part of it ANCOVA. But as soon as we added in an interaction, we wouldn't know what to do with that, so we lost its name. But this is basically why we call it linear models now. It's a linear model predicting the weight in pounds. So here, if we were to look at this model, I could see some plots here. This is our residual versus fitted values. There's no trend there. We like to see that. This model looks, this is the normality of residuals. Sometimes we check that as well. This is our, basically some other leverage parts, seeing if there's impactful points and so forth. But then what we really want to get to is our parameter estimates here. This is our frequentist estimate. One thing why I mentioned this is, I think, fake data is look at that R squared, 0.9787. If you have a diet program where you could describe the weight of a person with, where you have an R squared of 0.98, it's a pretty good diet program, right? I think that would probably work. But we have each of our point estimates. We can tell here the intercept is the expected value, the expected weight of somebody who's in the reference group of the diet group. So that would be group 1. And whose height is at the 0 point of height. Now I've considered height at 5 feet tall. So this is a 5 foot tall individual in diet group 1 is what we're looking at. So that mean is 147 pounds, right? So then, interestingly, take a look at this. The height in inches, for every 1 inch a person goes up, what does this represent? Anybody want to try to interpret that number? Yeah, but this slope, because it's part of an interaction, we have to consider what the interacting variable, where that it happens to be 0, right? So what this is telling us is the individuals in diet group 1, as for every inch they grow, for every inch taller they happen to be, we expect their weight to be less by 0.37 pounds. Does that seem reasonable? That sort of defies the laws of mass and physics. The taller someone happens to be, usually bones have weight, right? But who knows? Maybe that's just height because if you put your hat on, I don't know, never mind. Okay. We could say the same thing. Basically, if we were to say include that interaction, you might say what is the slope for somebody who's not in diet group 1, right? So what is the height slope for someone? And that's where this interaction starts to moderate it, right? And so we could show that the slope for someone in group 2 would be the sum of that slope plus this slope. And likewise for group 3. Similarly, what this grouping variable is telling us is here, diet group 2 is on average 24 pounds less than diet group 1, but because it shows up in the interaction as well too, That's only for somebody where the interacting variable is at 0. So for somebody who's 60 inches tall, diet group 2 expects their weight to be 24 pounds less, right? And so forth. Am I bringing back memories of interaction terms gone awry? Interactions are pains. They're hard. But let's put this into Stan, all right? This is what you can use for your homework. There's a point to this. I should have remembered that when I posted the slides, but I'll update you with an email about when things are posted. All right. In Stan, what I like to do is build the model first, right? Because the model defines all the parameters and the data that need to come in. So we go to the model block of Stan, and this is what I have. I put weight in pounds follows a normal distribution. Remember, it's normal because in a linear model, we expect the linear model to be, the outcome would be normal, conditionally normal, right? The mean of that normal distribution is formed by our regression coefficients times their predictor variables. And the standard deviation of that normal distribution is just a parameter sigma. So here, let's take a look. Weight in pounds is an observed variable. We'll have to import it. So we put it up here in weight in pounds. The mean, beta 0, that's a parameter, so we have to define it under the parameters block. Right? Likewise, beta in height is a parameter, but height 60 inches is an imported variable. So you go through each of the terms in your model, right here. Beta group 2 is a parameter. It's defined up in parameters. And then group 2 is an imported variable that equals 1 if a person's in group 2 and equals 0 otherwise. It's a dummy code. You can call it that way. Right? So we can do this for all the parameters. We can do this for all the observed variables. And you'll remember, when we import things in Stan, we have to declare the type of variable. When we define a parameter, we have to declare the type. So here, n is the number of observations. We need it to tell it how long our vectors are of data that come into Stan. N is also an integer. So when we define terms this way, Stan's going to want n to be a number that's 0, 1, 2, 3, etc., no decimal points. And the other values, when we describe them as vectors, are assumed to be floating point or real numbers. They can be any value. They can be positive. They can be positive. They can be negative. They can have decimal points. They just can't have imaginary numbers. They can't be what we call complex. Okay? There is a complex data type. I've never used it before. I feel like once I hit the real world of statistics, I'll start using imaginary numbers, but I've never found a place for them yet. Some people say latent variables are imaginary, but not quite the same way. Square root of -1 being the imaginary here. All right, let's talk about our parameters again. Each of the regression coefficients are real numbers, and they're unbounded, right? So they can be any value. And then sigma is also a real number, but it's bounded below at 0. So it cannot be 0 or below, right? So this is what we define to estimate. You'll note in this code, I actually didn't define prior distributions at all, which I think is bad practice, but I'm doing this just for the sake of discussion today. It's something where when we don't define prior distributions, what happens is Stan defaults to uninformative uniform priors, what it calls improper priors. Have I used that term improper? I feel like I have. An improper prior is a prior distribution that doesn't function like a full probability density. So an improper prior, if you think of a uniform prior, a uniform distribution is defined between two endpoints. And the space under that is every value is equally likely, but the curve has to equal, or the area under it has to equal 1. But since it's a rectangle, you can easily figure out what the height happens to be such that the area under it is 1. Well, in Stan, an improper prior across the real number line is called improper because we can't define a rectangle on infinite space, right? Because technically we're saying, oh, beta height goes from positive infinity to negative infinity, or the other way around. We cannot put a rectangle there because we don't know where infinity is. So, and this is getting a little bit in the weeds. Stan will call these improper priors, and in theory they are, but in practice, it turns out our computer actually knows where infinity is. I don't know if you've seen this before, But you can actually, in R, there's a dot machine object that tells you how much precision you end up having. And if you want to talk about the largest number possible, that's it right there in your R computer. All right? There's 300, move the decimal place 308 places to the right. Big. Right? Well, it turns out you can also define the smallest number possible. That's it. And what Stan is doing is putting a uniform prior between those two numbers on your parameters. So sometimes called improper, but not often. I like to call it proper because we actually use a computer to estimate this. All right, should we try to estimate this model real quick before we run out of time today? Let's do this. I'm going to build our Stan program. It'll compile. I have my Stan data. Remember, my Stan data object has every value in the data block of code listed in the list. And if I go sample this, I'm going to run a warm-up of 10,000 and sampling of 10,000. I'm going to run this analysis. And the next thing you know, my summary. Let's talk about convergence. First thing we need to look at. Did our model converge? One way that we can check this is to look at this table where R hat is 1. There's another quick way of doing that, which is to take the summary object and only the R hat value and calculate the maximum. All right, so the maximum R hat from all of our parameters is 1.000245. That to me sounds like we have a very well converged model. Anybody disagree? You want to see what it looks like with some plots? Let's do that. A rhetorical question, even if you don't want to see it. Sorry, it's my job to teach you this stuff. Maybe not. Maybe we won't see it. Come on, R, you can do this. And sometimes it takes a long time to plot these values because it turns out there's a lot of them. But here, LP, remember what LP was? It's our log posterior density. We don't often look at it. But all the other values are parameters that we're familiar with. So here, beta 0, height, group 2, group 3, height by group 2, height by group 3, and sigma. Does anybody think, any of these look suspect to you in terms of convergence? They look pretty good to me. I agree. So we can change that into histograms or densities. Right? The density is a smoothed histogram. So here is the density, a posterior density for each one of our parameters. And now we can describe their differences. And we can describe each of their values, not their differences, excuse me. Right? We could also compare these with the LM model as well too. And here in this box right here, you can see the difference, right? So our intercept, yes, question, JC. I think you're on mute, I'm sorry. Yeah, absolutely. What part? You want to see the Stan syntax or? Okay. Yes, right here. Good question. I didn't, just to show you it would run without them, but I should have, right? Yeah, it can. It's not advised. What's happening in Stan is it's setting a uniform prior on every parameter. And a uniform prior is, by definition, uninformative, right? A uniform distribution is flat for every value it could take. So I didn't put it on here in part because I wanted to compare and contrast what Bayesian is telling you with frequentist estimates and how close they happen to be. So the more I put a prior on, the more our Bayes estimates will turn, the more informative the prior, the more the Bayes estimates may affect the results, make them different from our non-frequentist values. But to my purpose in this beginning was to sort of compare and contrast the different approaches a little bit more. Thank you for your question. Okay. So here you can see not a lot of differences between the point estimates. The posterior mean, right here, the mean, this mean column is the posterior mean. The estimate is the value from the LM procedure. And you can see we're pretty close, within 1 to 2 decimal places for each. But where things do differ a little bit, but not a whole lot, but still differ, is our standard error. Our LM standard errors, the asymptotic standard error, is smaller than our Bayesian posterior standard deviation. And again, the reason for this is, again, that sigma in our model is allowed to vary. Right? It's reflecting the values of sigma in variance almost entirely. So here is a comparison of sigma. Now this is where things start to look, I don't know what you're doing there. Come on now. All right, I guess this isn't going to go. Here we go. So our LM estimate of sigma turned out to be 7.949 for its estimate. Now take a look at our posterior mean of sigma was 8.39. Our posterior mode of sigma was 8.23. Right? And our posterior standard deviation for sigma was 1.29. So when you run LM, all you get is your point estimate of sigma. You get no evidence of its variation at all. And part of what I'm showing this to you for is, in Bayesian, to do Bayesian well is to allow things to have its error to it. And so that's one key difference between us and frequentists when it comes to linear models. But second, I also wanted to describe, look at the shape of sigma's posterior distribution. The mean, again, is drawn toward the tail, the upper tail of sigma. The median's a bit closer, and had I described the mode of this distribution, which I can't do in the time that we have because we're out of time, that mode would be pretty close. And so what I would do later on, and what I'm going to show you when we get back, is what happens when I fix sigma to a value. Okay? But that's it for today. I need to stop, so I'll stop recording.